Good morning. Here is a quick review for exam 3. These are the important topics that you got to study in depth in order to do good on the exam. All right, here the first topic here is the force acting on a current carrying conductor kept in a magnetic field. So you have a current carrying conductor situated in a magnetic field, and we have to calculate the force on it. Obviously, the force is given by I, L cross B. So it's I times L cross B. It's a cross product. And here length may have 3 components, I, J, K, or just maybe 2 as given. And B could also have all the 3, but 2 may be possible like given. And let's say that the current is 2 ampere and we got to find the force. So it's 2 IJK and put the coefficients of the length first. First you have 2 for I, 4 for J, and nothing for K, so 0. And then put the coefficients of B, which is 0, 3, oh. All right, again, 2, 4, 0. 0, 3 minus 5, and then you take the cross product. I'm sure you know how to take the cross product. When you try to find the coefficient of I, you just go 4 times negative 5 minus 0 times 3, which is of course 0. So 4 times negative 5, that's negative 20. Well, when you do that for J, you're going to look at 2 times 10 to the negative 5. So that'll be negative 10. And for K, it'll be 2 times 3, which is 6. Okay, so I is 4 times negative 5, which is negative 20. And for J is a minus 10 because of 2 times negative 5. And K is 2 times 3 is 6, all right? And then distribute the 2, and you would get negative 40I plus 10J. No, that's supposed to be 20J. Okay, that is 20J there. So that is the 10 there goes off, and it's supposed to be 20J. Okay. All right, so plus 20J. And the next thing is, what's the direction of this force? So there are 2 sides to this. First, we find the magnitude of the force by this method. And next, we find the direction of the force using what's called right-hand rule number 1. Right-hand rule number 1. Let me show you that. In right-hand rule number 1, the thumb points in the direction of the current, as you can see. The thumb points in the direction of the current. And the fingers show the direction of the magnetic field, fingers, then the palm gives the direction of the force. So it's very clear that the force is perpendicular to the plane containing I and B. See, it's perpendicular to my palm out. So that's right-hand rule number 1, used to find the force on a current carrying conductor placed in a magnetic field. And also remember, you could calculate the force by ILB sine theta, because L cross B is nothing but LB sine theta, where theta is the angle between L and B, which is the angle between I and B. Why? Because current flows through the length. So it's the angle between the length and B. That's topic number 1. Got it? Here we go into topic number 2. The torque on a loop situated in a magnetic field, which leads us to the principle of a generator. Because in a generator, you have a loop rotating in a magnetic field, okay? That is electromagnetic induction. So, but anyway, here is the torque. Torque is given by NIAB sine theta. What are the turns? N is the number of turns. All right, N is the number of turns, I is the current in amperes, A is the area in meters squared, and a theta is the angle between what? Area and B. Area. What's the direction of area? Always perpendicular to the loop. Keep that in mind. Okay. And out of this formula, NIA, that product becomes important because N times I times A is called the magnetic moment of the loop. So magnetic moment is represented by mu. It's NIA, magnetic moment. What would the unit be? Well, the unit of I is ampere and area is meter squared. So magnetic moment would be in ampere meter squared. Well, if that be the case, if NIA is mu, then we have mu B sine theta, which is nothing but mu cross B. See how that works? Mu B sine theta, which is mu cross B. So you can also calculate the torque as the cross product of magnetic moment and the magnetic field. So here is a simple problem. Number of turns is 10. If the current flowing is 2 ampere and the area is 0.3 meter squared, well then the magnetic moment is 6 ampere meter squared. That's quite high because the area 0.3 is actually a big area. That is the torque on a current loop. All right, so that's topic number 2. On to number 3. A charge moving through a magnetic field. Now we got to be careful here. We are assuming this is a positive charge, especially when it comes to direction. You always state it with respect to a positive charge. So if it's a negative charge, the direction will be opposite. We'll get there. First of all, the magnitude of the force is Q, V cross B. What's Q? The charge of the particle. V is the velocity of the particle and B is the strength of the magnetic field. Now this can also be written as QVB sine theta, where theta is the angle between velocity and magnetic field. So that's how you calculate the force on a charged particle moving in a magnetic field. But sometimes you will not be given the velocity of the particle directly. You will be given the voltage through which it is accelerated. So when a charged particle is accelerated by an electric field, it picks up a velocity. So be careful that this caps V here is voltage. Little one is velocity. So if that's the case, you know the electrical energy, Q times the voltage, becomes the kinetic energy. So the electrical energy becomes the kinetic energy. So that's conservation of energy, from which you can calculate the velocity. Just rearrange that, calculate the velocity, and here is an example. Suppose it's a proton. Well, proton and electron have the same charge, only that one is positive, the other is negative. And let's assume that it's accelerated through 500 volt. You see the 500 volt. What is its velocity? Put in a calculator, you get it as 13.25 times 10 to the 6. Ooh, that is fast, yes. A tiny particle. Oh, wait a minute. This cannot be a proton because I took the mass of an electron. So I'm going to go back, and I'm sorry for that. This is the velocity of an electron accelerated through 500 volt. Why? Because I have taken the mass of the electron. So once you get that velocity, you can calculate the force acting on that electron. All right, so once again, you have, that's supposed to be 1.6 times 10 to the negative 19. There's a point there which you don't see, not very clear. Okay, so 1.6 times 10 to the negative 19. And then velocity we just got now. And let's assume that the magnetic field is 0.025 Tesla. Just made up that number. What happened to theta? Okay, if it's moving at right angles to the magnetic field, right angles, then theta is 90, sine 90 is 1. So I'm assuming that it moves at right angles, and that's when I get the force as 0.53 times 10 to the negative 13 Newton. Alright, so that's how you calculate the force on a charged particle moving through a magnetic field. But suppose you have the magnetic field spread out over a wider area, then the particle will be compelled to make a circular path. When it makes a circular path, we should be able to find the radius of that path. Why and how? Whenever any particle moves in a circular path, there is the centripetal force acting on it. In this case, the centripetal force is QVB. So we would put the two equations together to find the radius. Shall we do that? So here is the radius of the path of a charged particle through a magnetic field. That's the centripetal force. mv squared by r is equal to qvb. Rearrange and you get the radius as mv by qb. Okay, so the mass of the electron right there. We just found the velocity of the electron and then divided by the charge times the magnetic field, and you should be able to get the radius of the path. Obviously going to be very small because I took the magnetic field as 0.025 Tesla, which is a strong magnetic field. So it makes a tiny circle. If it's a weak magnetic field, it'll make a bigger circle. Those are the units: kilogram, meter per second, coulomb, and Tesla. You come up with 3.014 times 10 to the negative 3 meter. Isn't that small? Yeah. That's like 3.01 millimeter. That's very small. That's a small circle. Could we find the time period? That means the time taken to complete one rotation? Yes. How? It's the circumference over velocity, because time is distance divided by velocity. So if you do that, you're going to get 2 pi r, which is the circumference, divided by the velocity. And then you substitute for the radius. You know, radius is mv by qb, so substitute for that. And the velocities get cancelled out. So time period does not depend on the velocity. That's important to know. And then if you substitute the mass and all the other variables, you will get the time period, which I've not done, which is just simple algebra. So you see what happens, right? You understand everything about force acting on a charged particle in a magnetic field. Let's move on. Number 3, is it? Oh, before that, what about the direction of the force? I already gave you the right-hand rule before, but I want to show it to you again. There it is. Look at it. Especially the one on the right side. This one. Look at it. All right. So we are talking about a positive particle now. This only applies to a positive particle. The thumb gives the direction in which the velocity is. The fingers show the direction of magnetic field. The palm outwards gives the direction of the force. That's only for a positive particle. If it's for a negative particle, instead of taking it this way, take the force exactly opposite. Okay? So the negative particle is moving that way, magnetic field is that way. Instead of the force being out, it'll be to the back of the palm. That's for a negative particle. All right, so that's the only difference. And the diagram on the left side shows you actually how you could use the curl fingers, because it's V cross B. If you could take your fingers from velocity to magnetic field, curl it from V to B, velocity to B, then the thumb would give the force. Now, if that's confusing, just look at the one on the right side. So that's how you find the direction. Okay. What do we have next? This is the review for exam 3. So I hope you're listening. How do you find the magnetic field due to a straight conductor? So you have a conductor like this carrying current. How do you find the magnetic field? First of all, remember, the magnetic field is in the form of concentric circles around the conductor. Concentric circles. I'm going to show it to you in a few seconds. But the magnetic field depends on the distance. So if you want to find the magnetic field at distance d, there it is, at a distance d, then it's given by mu naught I by 2 pi d. I is the current, d is the distance from the conductor in meters. And you see that it's in the form of concentric circles there. And at this time, let me also say that the direction is given by right-hand rule number 2. There it is, right-hand rule number 2. What is that? Now you hold the conductor in your right hand with the thumb pointing in the direction of current, the closed fingers towards the nails. They give you the direction of the magnetic field. So if the current is up, looking from above, it's going to be counterclockwise. If the current is down, looking from above, the magnetic field is going to be clockwise. Okay, I hope you got that. It's also shown here clearly, so watch that, look at that. All right, what about magnetic field due to a solenoid? You know what a solenoid is? You have several loops on a cylindrical platform, and the loops are very close to each other. So you have a certain number of turns in a certain length. And how do you find the magnetic field at any point on the axis of the solenoid? So at the center of the solenoid, basically, it's mu naught little n I. Remember that little n is not the number of turns, but it is the number of turns divided by the length, which means little n is the number of turns in 1 meter. Okay, mu naught, it's 4 pi times 10 to the negative 7. It's called the permeability of free space. I is the current. So if it's a bigger current, then of course there is a bigger magnetic field at the center. And how do we find the direction? Okay, if you look at this diagram, and if you're looking at it from the left, facing this way, then the current appears to be clockwise. It appears to be clockwise. See that? If it appears to be clockwise, that's the South Pole, because you can write S, making it like a clockwise rotation. See that? On the other hand, if you look at it from this side, this side is going to be North Pole, because the current will appear to be counterclockwise. And N can be written that way. So that's how you find out where the poles of the solenoid are. So did the solenoid become a bar magnet? Yes, it did. It has exactly the same magnetic field as that of a bar magnet. And a bar magnet has a north and a south pole. So that's why I was trying to tell you how to find the poles. So you look at it from one end. If the current is clockwise, it's south pole. If the current is counterclockwise, it's the north pole. Let's move on. All right, what's coming next? AC generator. So what's an AC generator? It's a coil rotating in a magnetic field. There it is. That is the AC generator. You have a rectangular coil rotating in a magnetic field. And because it's cutting the magnetic field associated with the coil changes continuously. Therefore, by electromagnetic induction, there is an alternating current induced continuously. And that voltage that's induced is represented by either a sine or a cosine function. I've written a sine function, E is equal to E naught sine omega t. E naught is the peak value of voltage. And what is that? It's NBA omega, National Basketball Association omega. E naught is NBA omega. Okay, that's the maximum value of the voltage, or it's called the peak value of voltage. That's an AC generator. Simple. Then you have this all-important thing of applying an AC to an inductance, capacitance, and resistance. So if you apply this AC voltage to an inductor, a capacitor, and a resistor, one by one, or one after one, you get three important terms. You get, of course, for the resistance, it's just resistance, but for the inductance, you get what's called reactance. X stands for reactance. XL, inductive reactance, is 2 pi FL. Stop. What is L? L is the value of the inductance in henries. XL is the reactance in ohms. Okay, so XL is in ohms, like resistance. L is the value of the inductance. Similarly, for a capacitor, XC is 1 by 2 pi FC. What's C? C is the capacitance in farad. All right, and I just said Eli and ice. Eli loves ice. To remind you that in an inductance, the voltage comes first, followed by the current. So in an inductor, the voltage leads the current by pi by 2. Voltage leads the current by pi by 2. In a capacitor, on the other hand, I comes first. So current leads the voltage by pi by 2. Remember that. That's very important. They're totally opposite, aren't they not? What about the resistor? The resistor is passive. It's like voltage and current are going to be in phase. So they are in phase with each other. There is no phase difference. So when you put all three of these together in a series circuit, we get what's called impedance. Let's get there. Impedance contains resistance and reactance. Okay, so that's where we are headed to next. All right, so what do you see here? Through a resistor, the current and voltage are in phase. In an inductor, the voltage is leading by 90, so it's rotated in the counterclockwise direction by pi by 2 radians or 90 degrees. But in a capacitor, the voltage is behind the current by pi by 2 or 90, so that's why it's rotated clockwise. See that? And then to find the net, first you take the difference between these two vectors and then find the resultant with this one. All right, let me show you how. So that gives, the blue arrow gives the difference between XL and XC. Actually, IXL and IXC, okay. And that phi is the final phase difference between current and voltage. So understand, current is on the x-axis, positive, and the voltage comes out to be here, finally, and we have to find phi. As shown in this diagram, the voltage is leading the current by phi. Okay, we can find that very easily. So remember, that's XL, XC, XL minus XC. Technically, it should be multiplied by the current because it's voltage. But the currents cancel out when you take the ratio. So tan is going to be opposite side, which is same thing, XL minus XC divided by the adjacent side. XL minus XC by R. That's how you find the phase difference between current and voltage. And then impedance Z is square root R squared plus XL minus XC whole squared. So that's 2 parts to it. And at resonance, you know this part becomes 0. So impedance becomes equal to resistance at resonance. I've not written it, but you got to know that. And also at resonance, phi is 0 because XL and XC cancel out. That's why they became 0. So at resonance, the phase difference is 0. Just know that, okay? I've not worked out a problem with that, but that's very important, and try to work it out carefully, find XL, XC and all that. Electromagnetic induction is governed by Faraday's law. What is Faraday's law? The induced EMF is equal to the rate of change of magnetic flux. Flux is phi, so d phi by dt is the rate of change of magnetic flux. And what's the negative sign? It's the Lenz's law. There's one question on the Lenz's law. The direction of the induced EMF always opposes whatever produces it. So if the magnetic field is trying to decrease, then the induced current will set up a magnetic field in the same direction. Why? Because it was trying to decrease. It doesn't want it to decrease, set it up in the same direction. But what if the magnetic field was trying to increase? Then the induced current will set up a magnetic field opposite to that. Why? Because it wants to oppose it. Right? Because it was increasing, it opposes it by producing a magnetic field, right, in the opposite direction. I hope you're getting it. Okay. And then remember, flux phi is also related to current by this formula, Li. Phi is Li. That's where you get L, inductance, as phi by I. And what's the unit? Phi is in Weber, I is in ampere, and that's why the unit of inductance is Weber per ampere, also called Henry. Can we substitute that here? Yes, we can, of course. And then you would get E is equal to minus d by dt of phi. L is a constant taken out. So you would get E is minus L di by dt. What is that? Di by dt is the change in current, the rate of change in current. So whenever the current in a circuit increases or decreases, like in an AC, because it's continuously increasing and decreasing, there's always induced voltage. Okay, we're almost at the end now. Transformer. Transformers only work on AC. A transformer has a primary and a secondary wound on a laminated iron core. Okay, on an iron core. I think I have a diagram coming up. NP and NS are the number of turns in the primary and the secondary. VP and VS are the voltages. And it's a direct ratio. Wow, there is the diagram. It's a direct ratio here. But remember that here we have set the powers to be equal. So the power in the primary is equal to the power in the secondary. What is power? It's the voltage of current, and I meant to say it's the product of voltage and current. Product of voltage and current. And so that's why IPVP is equal to ISVS. I think it's the coffee that's all right, helping me out. So you see the transformer. So you have the primary coil here, you have the secondary here, and then you have the iron core, which is iron, of course. And then you have the primary and the... There you go. I've explained everything. Number of turns. If you look at this diagram, is this a step up or a step down transformer? How do you know? Look at the number of turns. More turns here, less here. It's step down. Step down. What does that mean? Oh, the voltage in the secondary is less. That means the current in the secondary is more than in the primary. It's an inverse thing. So remember that. Where are we now? An LR circuit, just like the CR circuit, the current grows and decays in an LR circuit. Inductance and resistance connected in series, remember that? So here are the formulas. Be careful. For growth, you have I is I naught times 1 minus e raised to minus RT by L. But when it's decay, you do not have the 1 minus. So it's only I naught e raised to minus RT by L. My camera turned off, so I'm going to continue without the picture because it's almost the end. I mean, my picture. Who cares about my picture anyway? So you have the growth and the decay, and then time constant. Time constant is L by R. Time constant is L by R. Then that's the graph represents, that's the time constant represented by tau. It's the time taken for the current to grow to 0.632 of the maximum. With that, we have come to an end. Now you know why I didn't care about showing my picture after the camera turned off. Because it was towards the end, and I hope this does you good. Go over this video several times, try to understand stuff. There's no use of writing stuff without understanding what they stand for and what they mean. Look at the units, look over this many times, and I am sure it's going to help you for the exam. Wish you all the best and take care.